In last few lectures, we have talked about interpolation. And by interpolation, what we mean is fitting of a curve exactly to a bunch of points. In particular, we have fitted polynomial type curves. Now, in this lecture, we'll talk about errors in polynomial interpolation. This is an advanced topic. To find the error, actually, we need some treatment of intricate mathematics. If you are not comfortable with that, you can actually skip this section and go to the next lecture. You will not miss anything in the exam and no continuity will be missed for subsequent part of this course. What we mean by interpolation error is as follows. Let us say I have a function y equals fx and I approximate this function as a polynomial px. This is the Lagrange polynomial. It is going through the points xi, yi, I equals 0 to n, this n plus 1 points. Since I know this function y equals fx and I have fitted this polynomial, then I should be able to calculate ex, which is fx minus px, and this difference is the error. Of course, in many applications, we don't know exactly the function. All we know are the points, and we are fitting polynomial through the points. And in those cases, we have no way to calculate the function, error function. But we'll have some idea that how much error could be in polynomial interpolation in this lecture. Let us take a function y equals fx in Cn plus 1 ab. Don't get intimidated by this notation. There's a complex notation Cn plus 1 ab. What it means that this function fx is continuous and it is differentiable up to n plus 1 order of differentiation. And those differentials are also continuous within this closed interval ab. Now, what we do is that for given xi, I goes 0 to n, I find this yi from this function, and that way I generate n plus 1 points xi, yi, which will fall exactly over this function. I goes from 0 to n, therefore this is n plus 1 points. Now I can use this n plus 1 points to fit an nth degree polynomial that will be given by a0 plus a1x plus a2x square, etc., all the way up to an x to the power n. You can see here I have a0, a1, a2 up to an, total n plus 1 unknowns, and I will use this n plus 1 distinct point. I'll let the polynomial pass through this n plus 1 distinct points, and that is how I'll get this a0, a1, a2, etc. up to an. So now that I have this polynomial, I can safely say that this polynomial is an approximation of y equals fx. It will match at exactly at this point xi, yi, but in other points it will not match. So this is an approximation of y equals fx. We are now ready to define an interpolation error, that is ex, which is given by fx minus px. Clearly, for x equals xi, this ex will be 0 because the polynomial is passing through these xi, yi points, and xi, yi points are calculated from this function. So function is also passing through these xi, yi points. So at these xi, yi points, the polynomial as well as the function, they will match exactly with each other. So the error is 0, not approximately 0, they're exactly 0. However, at other points there may be non-zero error, and we intend to find that out. So let us say we define a function of some variable t, which is gt equals et minus exk, product of t minus xi divided by xk minus xi. I goes from 0 to n. Here both t and xk, they are within this ab, but xk is a constant and t is a variable. T is the independent variable that gives us the function of t, and xk is just a particular point in that interval a b. So now you see that if I take t equals xi, I at this points i0 to n, then what happens? Here I have lots of t minus xi's at the top, and when t equals xi, all this t minus xi will be 0. So the second term of this gt, this term will be 0 for t equals xi. So this term will remain, exi will remain, but we know that exi is 0 because at x equal to xi, the polynomial as well as the function, they will match exactly with each other. So this e at xi is 0. So this is 0 at x equals t equals xi. Therefore, both the terms are 0. So g is 0 for I equals 0 to n. Now over and above, if t equals xk, where xk is not equal to xi, xk is a point within this interval ab, but we take that is not equal to xi. What happens if I put this t equals xi here, then each of this becomes xk minus xi divided by xk minus xi. So each of this becomes 1. So this will be 1 for t equals xk. So here what I will have this et minus exk, which will be 0 at t equals xk. Therefore, we can say that at t equals xk, where xk is not equal to xi, it is 0. We are not considering xk equals xi because we will fall into a problem because it is divided by this xk minus xi. So now we see what we have learned, that at all xi, this n plus 1 xi, g is 0, and then at xk, that is one particular value which is not equal to xi, there also g is 0. So g is 0 at this n plus 2 points, or we call it that this function z has n plus 2 zeros in the interval ab. This is an important idea and we'll use this idea. Now we go to a very important theorem is calculus, and we are not going to prove this theorem. The proof is not necessary here. We'll just state it. What it says that if g is a function that is continuous in the interval ab and it is differentiable up to n plus 1, if g is that kind of a function, and if it has n plus 2 zeros in AB, then what happens, this n plus 1th derivative of z will be 0 at some point within this open interval AB. That point we are giving eta. We don't know what point it is, but within this interval AB, if g has n plus 2 zeros, then n plus 1th derivative at least at one point, that will be 0. This is what is we call this generalized Rolle's theorem. You may be familiar with Rolle's theorem, where this n equals 0, actually that is the Rolle's theorem we are familiar with, but this is what is generalized. So this takes higher order derivative. Okay, let us now use this theorem. We have already learned that this g function, gt function, has n plus 2 zeros in AB. Then we also know that ex, that is fx plus px, and fx is n plus 1 times, we can differentiate them in AB. Px is a polynomial of nth degree, so we can differentiate it as many times as we wish. That is the good thing about polynomial. So both fx and px, they are continuous in AB and we can differentiate them up to n plus 1 time. Therefore, this ex is, we can say that we can differentiate ex n plus 1 time and it is continuous in AB. Therefore, g also, we can say that this is continuous in AB and differentiable n plus 1 time. Thus, using this theorem, we can now clearly say that this n plus 1th derivative of g at certain eta which we don't know will be 0. So at some point this derivative will be 0 within this open interval a b. Now what this derivative is about, I take this function here and I take a derivative n plus 1th derivative of this is equal to n plus 1th derivative of e minus e of xk. Xk is a constant, so e of xk is just a number, so we are not doing anything. E of xk, and here I have to take n plus 1th derivative of this product. So let's start with, this is an important idea and we'll look into it, but let's start with this en plus 1t. This en plus 1t is fn plus 1t minus pn plus 1t, because ex is fx minus px. So here I can write this is equal to fn plus 1t, since n plus 1th derivative of polynomial will be 0. Why? Because n plus 1th derivative of nth degree polynomial will be 0. You think about it, that if I take the first derivative, a0 will be 0. If I take the second derivative, a1x will go down to 0. If I take the third derivative, a2x square will go down to 0. Similarly, if I take the n plus 1th derivative, then anx to the power n will be 0. So n plus 1th derivative of px will be 0. That is why this pn plus 1t will be 0. So en plus 1t is coming down to f n plus 1t. All right. On the other side, I have this product of t minus xy divided by xk minus xi. So what we simplify in this way, the bottom part xk minus xi, I keep that is the product of I equals 0 to n xk minus xi. At the top I have n plus 1 t minus xi, because I have n plus 1 number of xi, t minus x0, t minus x1, t minus x2, etc. up to t minus xn. If I multiply this n plus 1 time, one term I'll get t n plus 1, of course. Then other term I'll get t to the power n, some constant, this bn, which we don't know, we can calculate from here, but there is no need to calculate it. Similarly, bn minus 1, tn minus 1, etc. up to b naught. I'll get this kind of an expression because I have n plus 1 number of t minus xi here. I am multiplying them. Alright, so now I'll take the derivative of this n plus 1th derivative. If I take n plus 1th derivative, nothing happens at the bottom. At the top part, I'll get factorial of n plus 1. Why? Let us see that if I take the first derivative, this b naught will go to 0. If I take the second derivative, b1t will go to 0. If I take the third derivative, t square will go to 0. If I take the fourth derivative, e to the power 3 will go to 0. Similarly, if I take the n plus 1 derivative, t to the power n will go to 0 after this. So when I take this derivative, I am only taking the derivative of t n plus 1. So what would be this t n plus 1 if I take n plus 1th derivative of that? That would be n plus 1 factorial. You can ask why. So for instance, if I take first derivative of x, that gives me factorial of 1. If I take second derivative of x square, that gives me factorial of 2. If I take third derivative of x square, it gives me 2 into 3, that is factorial of 3. So in the same way, if I take n plus 1th derivative of t n plus 1, that gives me factorial of n plus 1. Thus, we have both the expression here, en plus 1 is fn plus 1, and then n plus 1 is derivative of this product is factorial n plus 1 divided by this product of xk minus xi. So I come here and I write this gn plus 1t is equal to fn plus 1t minus e of xk, nothing happens here, this is a constant, n plus 1 factorial divided by this product xk minus xi. Now we know that at certain t equals eta, this gn plus 1 is 0. Therefore, I can write that putting eta in place of t, f n plus 1 eta minus this exk n plus 1 factorial divided by xk minus xi product. This will be 0. So I write this e of xk is equals f n plus 1 derivative at some point eta divided by n plus 1 factorial multiplied by xk minus xi product. This gives us as an expression of error at some point x equals xk. This is an error. So now we can generalize it, because this is the error at some point within AB. So if I generalize it for x, for any point if I take, I'll get at some point the derivative n plus 1 is derivative at some point which we don't know, multiplied by this product where this xi is within this interval AB, but where it is we don't know that. So this is the general expression of error. All right, then we cannot say anything very clearly that what the error is, but we are very sure that if my function this f n plus 1 has a tendency of growing with n, then we are likely to have a high error. We cannot say exactly because we don't know what this xi is. It will be somewhere the value of this f n plus 1, but if f n plus 1 is high, then the error will be high. We can also see that at x equals xi error will be 0. That is what we are expecting. But otherwise the error will be high where this derivative is high. So we have to be careful about functions with the value of derivative that is high. Now we know from this Weierstrass theorem, which is we are not going to prove here, that any function can be approximated by a polynomial. Now there is an important theorem in calculus known as Weierstrass theorem that says that any continuous function we can approximate that with a polynomial with arbitrary accuracy. So we can reduce this error as much as we wish using polynomial for any function if we are approximating it with a polynomial. But as we have seen that if f n plus 1, or in a sense that if the derivatives has a tendency to grow, then we have a problem, the error might go high. So the key is when you are doing polynomial interpolation, it to select this xi carefully so that error doesn't go very high, because we know that errors will be less near x equal to xi and errors will be 0 at x equal to xi. So where these derivatives will be high, if I can take this xi is close to those points, then we can still keep the errors low. So let us see an example here. One very important phenomena that we talk in terms of polynomial approximation error, that is known as Runge's phenomena. Let us say this is a function y by x is 1 divided by 1 plus ax square, where a is a constant. This function shows a very interesting behavior. Here I have plotted yx equals 1 divided by 1 plus 25x square, and this plot is this red line is the plot of the actual function. So this is our f of x. Now I am approximating that with interpolating polynomial. So I have taken this polynomial with uniform spacing with n equals 5. So we are interpolating with n equals 5, so that is 5th degree polynomial. If I take this 5th degree polynomial, you can see this blue curve is the 5th degree polynomial, and you can see the difference between red and blue are actually pretty high near these edges. There is also some difference here near the middle, but they are pretty high near the edges. So we hope that, well, if I go for a higher degree polynomial such as n equals 10, there may be less difference. So this green line is my n equals 10, that is 10 degree polynomial. You see here the error has actually increased. The error has decreased near the center, but near the edge the error has increased quite a bit. In fact, it is totally unacceptable type of error near the edge. So increasing the degree of polynomial doesn't help. What helps is that if we keep the spacing non-uniform, that means x0 to x1, x1 to x2, these are the spacing. When I keep the spacing uniform in this kind of functions, I get a lot of error. But when it is non-uniform, then let us say this black line is non-uniform n equals 10, and this green line is uniform n equals 10. The difference is staggering. The non-uniform x equals 10, this black line goes pretty close to this red line. So it's a good approximation. So if we can select this xi points carefully, then we can have a good approximation with polynomial. This is very much true for functions where derivative will grow within. So higher order approximation, here we see that there's a lot of oscillation which improves with non-uniform spacing. And this is a problem. That is why when we use higher order polynomial, we can see unphysical oscillation if we go with uniform spacing. And we have to do a careful study about the nature of functions, nature of point we are approximating before we can do interpolation with higher order polynomial. If we have no idea about the nature of function, then it is probably best not to do with higher order polynomial. In summary, we have seen that polynomial interpolation errors could be high for the functions whose derivative grows with order of differentiation. We can control this error by carefully selecting the interpolation points. For your exercise, you can use this Newton's polynomial or Lagrange's polynomial to approximate this y equals 1 by 1 plus 25x square in interval 1, 1, minus 1, 1. And you try with n equals 6, n equals 7, n equals 8, that means 6 degree, 7 degree, 8 degree polynomial. And then you repeat this exercise with non-uniform spacing, that is xi is minus cos I pi n, where I is 0 to n and n equals 8. So with this kind of xi, you try this and hopefully you will see a much better result with this non-uniform spacing. Why, of course, we take this cos I pi by n, that is a different discussion, and we will not take that discussion in this course, but you will find this kind of spacing will give you a much better result. That is all for this lecture. Thank you, and I'll see you in next class.